Alright, in this video I'm going to be going over the guided notes for 7.5. We actually covered the top part of this the other day in class, but I'm going to just start from the top and work through this entire page as a review of the things that we talked about before and just for anyone who might have missed that. So the first thing that we're going to talk about is what an exponential function is. So the definition we're going to work with is that it's a function in which the range, and the range are the y values, they have to have a common factor when the domain, which are the x values, increase by regular intervals. So an exponential function is a function that does not have a constant rate of change. If you remember back to lines or linear functions have a constant rate of change, which is the slope. And what that means is if we're looking at a line or thinking about a line, if this is just a little graph over here, the two main parts of a line are the slope and the y-intercept. The y-intercept tells us where we're going to start, so we could start, down here. And the slope tells us the direction, the steepness, the incline of this line. So if we have a slope of 3/2, that means we're going to go up 3 and over 2. So that would put us here. And we're going to continue that pattern, up 3 over 2. And from here we can go down 3 over 2. And that is what, sorry, that point wasn't very good. It's not really in line. But this is what gives us our line. And if at any point we don't have that same constant rate of change, say we go, up 5 over 2, like it ceases to be a line, it starts to become a curve or something else. So a line has a constant rate of change, which is the slope. But now we're going to start looking at functions that don't have a constant rate of change, but they do have different kind of relationship with their x and y coordinates. So exponential functions are a special type of function where the range values have a common factor. And what I mean by factor is if we're moving from one y value to the next and we're trying to find a pattern, a common factor means we're going to be multiplying. I don't need to think that's an x, so we're multiplying to get from one to the next. And we're multiplying by the same number over and over again as we go from y value to y value. And the domain, or the x values, are going to increase, or they could decrease by regular intervals. Meaning if we're going from one x value to the next, we should be adding or subtracting the same number every time. And this is actually the same for whether we're looking at a line or whether we're looking at an exponential function, or really any function, because we're the ones determining the x values. We want them to increase or decrease by regular intervals so that we can see what kind of relationship we have between the y values. If the y values also have a constant rate of change, meaning we're adding or subtracting the same amount each time, then we're going to have a line. But if we're multiplying or dividing each time, we're going to have an exponential function. And then there's many other functions that we'll get into some a little bit later, or in geometry or algebra 2, you'll learn about all kinds of functions that have a different relationship between their x and y values. So the first thing that we're going to do here is learn how to determine, or we're going to look at an example of determining whether the set of data shown is exponential or not. So here's our example. So the first thing I'm going to do is check out the x values. The x values need to increase by regular intervals, as it says right here. So I'm looking for that I'm adding or subtracting by the same amount each time. So from 0 to 2, that's a plus 2. 2 to 4, that's plus 2. 4 to 6 is plus 2, plus 2, plus 2. So we check the box here. Yes, our x values are increasing by regular intervals. So that means this could be really any kind of function. We're looking for a specific relationship, though, between the y values. So when I look at the y values, this is really going to tell me what's going on. So when I plug in 0, I'm up at 64. So then when we go over 2, I'm down to 32. So it looks like this is a pattern of minus 32 possibly. But then if I go from 32 to 16, that is not a minus 32. That doesn't work. And from 16 to 8, that's definitely not a minus 32. So we don't have a constant rate of change here. We're not subtracting by the same amount each time. But let's see if we can find a different pattern or relationship. So from 64 to 32, I know that it's being cut in half. So 64 divided by 2 is 32. And 32 divided by 2 is 16. And 16 divided by 2 is 8. And 8 divided by 2 is 4. And 4 divided by 2 is 2. So it does look like we have this idea of a common factor. Now, when we're talking about a common factor, we want to think of it in terms of multiplication. So instead of saying divide by 2, what I can actually say is that I'm multiplying by 1/2. I'm cutting this in half. And if you don't believe me that 64 times 1/2 is 32, go ahead and plug that in your calculator and see what you get. And then 32 times 1/2 is 16. And 16 times 1/2 is 8. And 8 times 1/2 is 4. And 4 times 1/2 is 2. So we do have a common factor. We're multiplying by the same number over and over and over again. So the answer to this question would be yes. This is exponential. Because, and we want to explain our thinking here, and I'm going to refer exactly to the vocabulary I learned in my definition here. This is exponential because as the x values, what's happening with them? They're increasing by 2. So as the x values increase by 2, the y values have a common factor of 1/2. That means we're multiplying by 1/2 to get from y to y. So pay attention to my vocab here. I said x values increase by 2, and the y values have a common factor of 1/2. That vocabulary is very important. So even though this may seem like a little bit of writing, please write it down exactly like that, because this vocabulary is very important, and it will help shape our understanding of what's going on with these type of graphs. So as opposed to this linear function over here, what's happening if I draw like a little graph of this data over here, and actually you may notice that we have all positive numbers for y, so I'm actually going to drop the axis down to give myself a little more space. But you might notice that at 0, I'm up at 64, big number. And then when I go over 2, then I'm cutting in half. So if I cut 64 in half, that's about there. And then when I go over to 4, I'm cutting that in half. So I'm about here. And then when I get to 6, I'm cutting that in half. So I'm even lower. And it's getting lower and lower and lower and lower. And I'm just cutting in half, 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 half. And so my graph takes on this shape right here. Oops, got a couple bumps in there. I'll try and smooth that out. So whoops, and then I missed it. Here we go, one more try. There we go. So our graph has a shape like this, and we can tell that this is not a line in the sense that it's not a straight line. This is definitely a curving graph, and it's decreasing, it's going down, and that has to do with what our common factor is. So now we're going to get a little more into the graphs of these exponential functions and the functions themselves. So an exponential function is in the form, like a line is in the form y equals mx plus b. An exponential function is going to look like y equals a times b to the x power, okay? So when we're plugging in our x value, we're actually plugging it in as an exponent. So that is quite different from our equation of a line, which is y equals mx plus b. So exponential functions always have, okay, here's a note down here. Exponential functions always have a horizontal asymptote because when you raise a number to a power, it will never be less than or equal to 0. So here's a point, and actually I realized that I skipped a vocab word right here. So something that we have with exponential functions are asymptotes. An asymptote is a line that the graph gets close to but never touches or crosses. So if we look at the example that I just did over here, as we continue to plug in x values and we get cut in half, 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 we can keep cutting a number no matter how small a number gets, we can continue to cut it in half forever and ever. So there's nothing I can ever do to cut a number in half and get 0. Because even if I cut a very small number or amount of something in half, it's still going to be an even smaller amount. So if we look here, this is a great example that this line y equals 0, this exponential function is never going to touch this 0. It's going to get closer and closer and closer forever, but it's never going to touch this line. It's never going to hit the 0. And that's what an asymptote is. It's a line that the graph gets close to, but it's never going to touch it, and it's never going to cross over that. And this point down here just kind of explains why that is. So exponential functions are always going to have a horizontal asymptote. That means like a line, a horizontal line like this, that the graph is never going to touch. Because when you raise a number to a power, it will never be less than or equal to 0. So that's just a side note. You'll see that these functions will all kind of have a shape, and then they'll curve and they'll get closer and closer and closer to a certain line, but they're never actually going to touch that line. So now we're going to look at some examples of different kinds of exponential functions. So we can categorize exponential functions in 2 ways. We can classify them as exponential growth and exponential decay. So the first one we'll look at is an example of exponential growth. And it is what it sounds like. When we're growing exponentially, it means that our values are getting bigger and bigger and bigger. So if we're looking at our function y equals a times b of x, growth happens when that b value is a whole number. So when b is a whole number, we're raising a whole number to a power, it's going to be getting bigger and bigger. Imagine if we had, let's just do an example. So if I have y equals 2 to the x power, we have this base of 2. It's a whole number. B is greater than 1, so this is a whole number. When I'm raising a whole number to a power, I'm just going to keep getting bigger and bigger. So like 2 to the first power is 2. 2 to the second power is 4. 2 to the third power, 2 times 2 times 2 is 8. So this just keeps growing and growing and growing. So that's why this is an example of exponential growth. And when we're dealing with growth, our graph is going to be increasing. So it's going to be going up like this. So the way we can see what this looks like is we're going to plug in some x values into this function and create a table of values that we can then plot on our line. So for this table, we're usually going to stick to values. I like to use the values -2, -1, 0, and then 1, 2. So what I'm going to do is your x values are always values that you are choosing yourself. And then the y values are what you're going to solve for. So in order to solve for y, I'm going to plug in this value for x, which is the exponent. So actually, let me change that color. So I'm going to plug in -2 for x, and I'm going to solve for y. So that means I'm doing 2 to the -2 power. So 2 to the -2 power, if we remember when we were doing rules of exponents, when we're raising something to a negative power, that actually means that it's going to be sent to the bottom. So this means that I need to move this down to the bottom and put a 1 on top. So I have 1 over 2 squared. 2 times 2 is 4. Obviously, if you have a calculator, you can also plug that in. You just plug in 2 and then use the caret symbol, and then you plug in a -2, and you'll get 0.25, and then you can press math enter, and you'll get 1 over 4. Actually, let me see if I downloaded a calculator. I can show that on here. Whoops. See if I can get in here and show you how it's done. Okay, so it wants me to look at it this way. So how I would plug that in is to this symbol right here, it's called a caret, to the -2, enter, and you get 0.25. If you want to see that as a fraction, you would press math, enter, enter, and that's 1/4. Or you could use your knowledge of negative exponents to solve. So hopping back over here to the notes, I'm going to now plug in -1 for x. So I have y equals 2 to the -1. So once again, if I have a negative exponent, it needs to go to the denominator. So I have 1 over 2 to the 1, which is just 2. And you can once again check that by plugging it into your calculator. I'll show you one more time. So this time we're going to go 2 raised to the -1, enter, and you'll get 0.5. If you press math, enter, enter, you get 1/2. I don't care if you keep it as a decimal or if you put it as a fraction, whatever makes most sense to you in terms of graphing, because that's what we're going to be doing next. So now I'm going to plug in 0 for x. So I'm going to have 2 to the 0, and we know that anything raised to the 0 power equals 1. Now I'm going to raise 2 to the first power, so I have 2 to the 1. Well, that just means I have the number 2. And then I'm going to raise 2 to the second power. So 2 to the second power means I have 2 times 2, which equals 4. So now we're going to actually plot these numbers on a graph. So we have this graph over here, and please notice that it is counting by 2s. So I've got 1, 2, 3, 4, 5, 6, and same on the y-axis, 1, 2, 3, 4, 5, 6. So we're going to plot these as x comma y. So for this one, I have -2 comma 1/4. So I'm going to go down 2 and then up 1/4, which is just up, like not half of half. So just right there, a tiny little dot. My next point is -1 comma 1/2. So I'm going to go to -1 and I'm going to go up a half, right like this. Then I'm going to go to the point 0 comma 1. So at 0, I go up 1. Then I'm going to go to the point 1 comma 2. So 1 comma 2 puts me here. And then 2 comma 4. 2 comma 1, 2, 3, 4. So already you can see the curve of this graph. It looks like it's starting down low and it's going up. Up, 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 up. And that's going to continue to grow. So this is an example of exponential growth. It's getting bigger and bigger and bigger. And it's going up, it's increasing. So to answer these questions, we can say it's exponential growth. We'll circle that. When we're talking about the domain of this function, it means that we want to know what the domain is, the x values. So what values of x are possible? Well, this is going to continue going smaller and smaller and smaller. So what's happening here is x, we could plug in any value of x we want. We could plug in -1,249. That's going to give us a tiny, tiny, tiny number for y when we solve that, but we can plug in any x value we want. And the same way, we can plug in as big of a number as we want. We could plug in a number 249,648. And obviously that's going to give us a huge y value, but the idea here is that we can plug in any value for x that we want, and it will work. So the domain here, and there's a couple of ways of writing this, but it's all real numbers. That's our domain. All real numbers. In other ways, you could say it goes from -infinity to +infinity. That's another way of saying every number. You can plug in any number from -infinity to +infinity and it will work. So that's our domain. Now the range is the y values. So we've got to think about this one a little bit, because y values are going from down here to up here. So from bottom to top. Now if you notice, this graph, as we look to the left this way, it's not really going down more. And remember up here we said exponential functions will have a horizontal asymptote like this. And so it appears that this graph, the larger a negative x value we plug in, we're going to get smaller and smaller and smaller and closer and closer and closer to the y, to this, y equals 0 line, but it's never actually going to touch that line. So what that means is this pink, our graph here, is never going to go down here. It's never going to go below that line. So the range, and then if we go up, this graph will continue to go up and up and up and up for infinity. So the range of this graph is that y values have to be greater than 0. This graph is never going to be less than 0. It's never going to cross this line. And another way you can write this, you can say it's going to go from 0 to infinity. And when we're talking about y, we're talking about the up and down. And when we're talking about the domain, we're talking about left to right. So that's a kind of new idea that we're going to have to practice a little bit. So talking about the y-intercept, we know this from dealing with lines. Y-intercept is where this graph crosses the y-axis. So it is the point, if we have our graph like this, the y-intercept is where we cross the axis, okay? And it's at the point where x equals 0. So it's that point right there. So if we look, it looks like it's crossing right here. And if we look over at our data, when x equals 0, y equals 1. So we have a y-intercept at 0, 1. And then our asymptote, that is remember up here in our vocab, it's a line that the graph gets close to but never crosses or touches. Our asymptote is right here, and that's a straight horizontal line. If you remember HOI, a horizontal line, it means it's y equals something. So in this case, it's y equals 0 because it's at 0. So y equals 0, that's our horizontal asymptote. So now we're going to look at a second example, and this example deals with decay. So what do I mean when I say decay? I mean that in these examples, we're looking at a b value that is between 0 and 1, meaning it's a fraction or a decimal. And these graphs are going to be decreasing. They're going to get smaller and smaller and smaller. So instead of going up, it's going to be going down. So an example of this would be the graph of y equals 1/2 x raised to the x. So what we're going to do here is we're going to once again choose our own x values. So I'm going to once again choose values -2, -1, 0, 1, and 2. And we're going to plug those in for x. So first I'm going to plug in -2 for x, and I'm going to see what I get for y. So I'm going to do 1/2 raised to the -2 power. So this one you probably want to plug in your calculator, and notice how I used parentheses over this fraction, just like it's given in the example. That's important. So when we go to our calculator, we're going to use those parentheses. And I'm going to do 1 divided by 2, 1/2, close parentheses, raised to the -2. Enter, and I get 4. So the answer to this is 4. Oops, I want my screen to turn back. There we go. So 1/2 to the -2 is 4. Next I'm going to plug in -1. So I have 1/2 to the -1. So once again, let's check this in our calculator. I'm sorry if this is sideways for you, but so I'm going to do 1 parentheses 1 divided by 2 and parentheses. I'm going to raise this to the -1. Enter, and I get 2. So I get 2. I'm going to plug in 0, so I have 1/2 to the 0, and it doesn't matter what it is. If I'm raising it to the 0, I'm going to get 1. And then I have 1/2 raised to the 1. Anything raised to the first power is itself. And then when I plug in 2, I'm going to get 1/2 squared. Well, 1 squared is 1, and 2 squared is 4. So these are my new y values. And as you can see, instead of getting bigger and bigger and bigger, these values are getting smaller and smaller. So I'm going to graph these. So the first point is -2, 4. So I'm going to go down 2, up 4, 1, 2, 3, 4. And then my next point is -1, 2. Oops. So I'm going to go to -1 and up 2. My next point is 0, 1. So at 0, I go up 1. My next point is 1, 1/2. So I'm going to go to 1 and go up 1/2. And then my last point is 2 and 1/4, 2, 1/4. So I'm going to go to 2, and I'm going to go up 1/2 of 1/2, which is just barely up. And as you can see, this line has a shape where it's going down, 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 but then it kind of levels off and it's going to keep getting smaller and smaller and smaller. But just like the example we started off with, I can keep cutting things in half forever and ever and ever without touching 0. So once again, we have an asymptote here on y equals 0. This graph is going to forever get closer and closer to this line, but it will never actually touch it. So now we can answer the same questions we answered before, but for this graph. So this is an example of decay because it's going down and it's decreasing and getting smaller. The domain, the x values here, well, once again, if we're thinking about x values go from left to right. This is going to keep going gradually. We can go back and back and back and back. So this is going to go back forever, and then this is going to keep going to the right forever. So we can have all real numbers. We can choose anything we want for x. The problem is when we get to the y values, the range values, when we're looking up and down. So obviously this can go up and up and up forever, but it cannot go down and down and down forever. It's never going to cross over this line down here. So the range, if we're going from least to greatest, once again, y has to be greater than 0. It has to be above this line. And so that's how you can write it. You can also, once again, say that y is going to go from 0 to infinity. So it's going to start here at the line, and it's going to go up and up and up forever. The y-intercept is where this graph crosses the y-axis, which is this point right here, which is 0, 1. 0, 1. And the asymptote, that is this line right here that it's never going to touch, that is a horizontal line, hoi, so it's y equals 0. Okay, so I know that was a lot of information. Thankfully, we kind of already discussed and went over the top part earlier, so it's just this graphing and this vocabulary that's going to be new. So next up is going to be a video going over the skills 4, 5, and 6, so stay tuned for that.